Hello everyone, my name is Chirag Patil and welcome back to my YouTube channel. So this is another video of LLM series in which we will see what is embedding and which kind of embedding technique is used in the transformer, right? So in previous video we had seen a tokenization technique, right? In detail byte pair encoding, right? If you recall a transformer architecture in that after the tokenization we need to convert a token into embedding, right? So let's understand what is it. So at core level, embedding is nothing but a way of representing a words or token or even a sentences as a vector. Okay, in a continuous space, of course. So these vectors are learned during the training and capture the semantic relationship between the words. So if I simplify it, so basically a vector of word which has a similar meaning should have at the less distance, right? Okay, so let's suppose I am using two words, okay, let's say car and vehicle, okay, and I will represent them into a, let's say, dense vector or some kind of vector, okay. Let's say this dimension is 1 cross 10 and this also has 1 cross 10 dimension, okay. So we have a vector for two words car and vehicle. So as we know, car and vehicles are similar, right? So when I take a distance between these two vectors, right, it should be a smaller. In other words, if I take the cosine similarity between these two vectors, it should be higher, right? Same way, if you say king and queen, they should have smaller distance or high similarity than king and table, right? Because king and table are very different words, right? They don't share any kind of meaning, right? So our task is basically convert our word, token, or a sentences even into a vector representation which contains a contextual meaning of it, right? So now let's see what are the ways to convert a token into a vector, right? So first and simplest way is one hot encoding, okay? So in one hot encoding, what we do, we will represent each word as a binary vector, basically 0 and 1. Okay. Based on the vocabulary. How? So let's suppose I have a vocabulary of 5 words. So if you have seen the previous video of tokenization, you can recall what is vocabulary and what is vocabulary size, right? So let's suppose in my vocabulary I have only 5 words. Let's say the cat sat on mat. Okay, then I will assign the id to each word, okay. Let's say 0 1 2 3 and 4. So these are the 5 words, okay. So simply I will create a one vector of dimension 5, and let's suppose I want to represent word the, right? Then at the first index or 0th index, basically I will put 1 and rest of them will be a 0. Same for the car, as car has the 1 id, right? So at the first index, basically 1, we will place it 1 there, right? So this will be a representation of cat, right? So if you see, we are able to convert a word into a vector space, but this does not contain any kind of contextual meaning, right? We are treating each word independently, right? Just providing the id and converting into a vector, right? Basically sparse vector. If you say we have a vocabulary of 1000, right? Then we have 1 cross 1000 dimension vector, and only one place has the 1 and rest of them has 0, right? So it is very sparse matrix, right? So these are the limitation of it. They ignore the word context and fail to capture the synonyms, right? So as we are not treating the contextual meaning, it won't be able to understand synonyms, right? And third point is it does not handle out of vocabulary word. Now what is the out of vocabulary word? It's simple. You had created a vocabulary of 5 words, right? Let's suppose in the prediction time you are facing or you are getting a new word. Let's suppose a car. Okay. Then how you will create a vector for car, right? You cannot create because you had already defined your vocabulary, right? So it cannot handle out of vocabulary word by default, right? So there is a technique, like you can use the tokenization technique like that it can handle the out of vocabulary word, right? So this is the simplest way. Now let's see, as I say, it create a very sparse matrix, right? So let's see the way of creating a vector in the dense type, right? So there is a technique called word to vec. So this technique basically map word to the dense and lower dimension vectors where similar words are closer together, right? So here if you see in one hot encoding, right? If we have a 10k words, we require a 10k dimension vector, right? But here these techniques are independent of vocabulary size. They will create a fixed size of embedding. You can decide like is 64, 128, 256. As this dimension is higher, the embedding store much rich information about that word, right? And these are the pre-trained embedding basically. So what does the pre-train means? So you are training one kind of model and it will create the embeddings and you will store it. And whenever you need, you will reutilize it, right? So this is basically pre-computed or pre-trained. Now let's see how these vectors are generated, right? So one of the techniques is word to vec and it uses two approaches. One is SIBO, continuous bag of word, and second is skipgram, right? So let's see how this SIBO works basically, okay? So if I say this technique is based on the neural network, so we are training one neural network, right? So now the question is, what is the input of that neural network? What will be the output? And what will be the architecture, right? So let's see first of the input data for the model, right? For the embedding model in the SIBO. So for SIBO, we will require two things, okay? First, let's say context word, and second will be target word, okay? So now what is the context word and what is the target word, okay? So let's suppose I have one sentence, okay? Let's say same sentence, the cat sat on mat. Now let's say I have context window. Let's say context window is equal to 1. Simple. So then what we'll do, we will pick one word, let's say this one, and we will see the one word at the left side and one word at the right side. Now these two words will be our context word. So let's suppose the set, these two will be our context word, and for it cat will be our target word, okay? Same if we go toward the set, then cat on and set, this will be our target word, this will be our context word. So we will train a neural network such a way that we will provide this as an input, right? Let's say the and set as an input, and model will try to predict the cat. In simple way, we will provide the context words, and based on that context word, model will try to predict a target word. Okay, so this is a input and output for that model in SIBO. Okay, so now let's see how we are applying this. Okay, so this is a simple architecture of of the SIBO. So let's suppose here we had used context size of 2. So we will use two words left and two words from the right side. Okay, so in our same example, it will be, let's say, the cat on mat, and our target is predict, which we need to predict is, let's say, word a set. Okay, clear? So here first of all we will convert this word into one hot encoding. Okay, so most of them will be 0, right? And let's say 1 will be 1 here. Okay, any one dimension. Okay, for the cat same we will use the similar thing, and so on. right? We had converted this into one hot encoder, and then we will create a simple ANN with one hidden layer, okay, here, and the output will be the softmax of the size vocabulary, okay. So let's say in my vocabulary I have 1000 word, then it will be the size of 1000 softmax simply, right? And it will predict the probability of each word as a target word. When we train, this set should be has the highest probability right here. So if you see, we are training this neural network, and these are the dense connection, okay. So let's suppose we have 1000 word, okay, then this will be 1000 cross this hidden layer size, and this hidden layer size is nothing but our embedding size, which we need to decide, right? Let's suppose we will use 64, right? Then if you see, this connection will be 1000 cross 64. Same, this connection will be also 1000 cross 64, 1000 cross 64, 1000 cross 64, right? So now we will train this neural network, which will take context words, predict the target word, right? So now after training, if you say, we will get this matrix, right? 1000 cross 64. Let's suppose I am selecting this as of now, okay. So I will have 1000 cross 64. Only take this part, okay. So if I will provide the one hot encoding of the, right, then I will receive 64 dimension matrix, this one. If I will provide one hot encoding of cat here, I will again get 64 dimension, right? So I will apply one hot encoding for each word and take this 64 dimension value as an embedding, and I will create my own embedding vector or embedding matrix for my vocabulary, which will be 1000 cross 64, right? Clear? So there is one catch here. So if you say I had selected this one, right? But someone can say I want to select this one because it is also 1000 cross 64, right? This is also 1000 cross 64 and this is also 1000 cross 64. Now which one we need to select? So when we train a neural network, we will force this all weights to be same. Same, that means this 1000 cross 64 weight will be same as this, will be same as this, and will be same as this. So you can pick any one, right? So this is how a SIBO model can be trained, and we can get pre-computed embeddings for words, right? And how we can train this model? We will train this model on larger data set, like we can use Wikipedia data set, right? Or we can use any text available on the internet, right? So this is how SIBO works. And second, there is another thing which is called skipgram, right? So in skipgram, we are doing a reverse thing. From target word, we will try to predict context words, okay. So you will provide a one hot encoding of any one word. Here we will provide, here we will provide one hot encoding of set, and we will try to predict here, let's say the cat on mat, right? It is the reverse. So if you see, the skipgram is very hard to train, right? Because from one word we need to predict the multiple word, right? So this is how the skipgram works, okay. So if you want detailed video on SIBO and skipgram, please let me know in the comment section. I will create a dedicated video for it, right? So this is how we can create embeddings using a deep learning technique, right? Now there is a third thing or third way to create an embedding is use the embedding layer, okay. Let me zoom it a little bit, okay, yeah. So there is a way to use embedding layer, right? So embedding layer, you can treat it as a trainable layer which learn how to map tokens or words to particular vector space, right? Which is the embedding. So if you see here, whenever we use word to vec algorithms, right? We need to provide a one word and we will get the embeddings, all right? Simple. So it is pre-computed. But what if we have different data than the model trained for the word to vec, right? Let's suppose this is trained on the Wikipedia, but I have some requirement of medical related text, right? Then this might not have my words which I want to embed, right? So at that time, this embedding layer will be helpful. So now how this work, embedding layer will work, okay? So first of all, we will tokenize our sentence, right? Simply. And then we will assign a ID to each token. So now we will provide a array or sequence basically containing the ID of the words. So if you see here what we are doing, we are providing a one hot encoding for each word, right? But here we will not provide a one hot encoding for each word, but we will just assign a ID, right? So if for example I have sentence I love NLP, it will be converted into a vector which contains only the integer IDs for particular word or token. Okay. So here if you see I has the 0 ID, love has the 1 ID and NLP has 2 ID. Okay. Now there will be an embedding matrix of size vocabulary cross n. Okay. So this is the vocabulary size and this is n. N is nothing but your embedding size. Okay. Which you will decide how much length of embedding or how much shape of embedding you need. Let's suppose we want 128, right? Then this matrix will be trained during the training based on the back propagation of the model itself, okay? And we will find our embedding, right? So when we will pass the token index and we will get embedding simply, right? So what is the benefit of this basically? So unlike pre-trained embeddings, this embedding layer are fine-tuned for specific tasks, right? So we don't care about on which this my word to vec is trained. We don't need to use that basically, okay? We have our own embedding model, or you can say embedding layer, which is trained along with the model on the data which we want, right? Simple. And second, dynamic vocabulary handling, right? So if you use the first point is if you use a pre-trained word to vec model, you need to have fixed vocabulary, right? If that word to vec model does not contain your word, you will not get embedding for it, right? This is the first point. Second thing, as we are using this as a part of model, so we have our own vocabulary. Second thing, we can use subword tokenization techniques like byte pair encoding, which we had learned in the previous video, to handle out of vocabulary words, right? And another benefit of it is the part of neural network architecture, right? We don't need to manage two things. One is the embedding model and second is our model, right? So it is the part of our model, so we can manage it very efficiently, right? And it is the part of end-to-end training, so it has already seen whole training data, right? And another is it can handle subword and character. Okay, so if you had trained, let's say SIBO on word level, right? Then you cannot utilize it for the character level, right? And same, if you had trained it for the character level, let's suppose, you cannot use it for the word. But here, as we are using byte pair encoding, right? It will convert our text into character level, subword level, and word level, right? So when we use embedding layer, it can work with all of them, right? Because we just need to pass a ID of token, right? Rest will be trained by the model. So that's why this is the best technique to use embedding, and this is the technique which is used in the transformer architecture and LLMs. Okay, so they are using an embedding layer itself, which is a second layer. First we have the tokenization, then we use the embedding layer, right? And there is one more thing about the embeddings. We can create embedding of sentence or even a document itself. Okay, so let's suppose I have two sentences. Let's say I am fine. Okay, second sentence is I am good. So we can convert this whole sentence into a vector of dimension anything, let's say 768. Okay, which this embedding basically contains the whole meaning of this sentences. Okay, and if I calculate the cosine similarity between these two vector will be higher, right? But to understand how it is generating this sentence level embedding, we first need to understand how the architecture of the transformer, because the models are used for this is the BERT basically, right? And which use a transformer architecture. So once we learn the architecture of it, we can see how these sentence embeddings are generated and how it contains the whole meaning of the word, right? Okay, so this is about embedding in the transformer, right? So if you have any doubt or query, you can ask in the comment section, we can discuss there. And if you like this video, please press the like button and subscribe my channel for more content. And please press a bell icon to get the notification whenever I will upload the new video, right? Thank you.